Good morning, everyone. So, in this video, we are going to see about the biological neural network and artificial neural network structure and their terminologies. So, coming to the biological neural network, here we are having the inputs and we are having the outputs, and in between, we are having the axon trunk. So, this will carry the information from inputs to the output side. So here we can call the inputs as the dendrites, and we can also call outputs as the synapses, and the outputs of one neuron will be feeded as the inputs to the another neuron. So that is why here we can say inputs equal to synapses also, and we can also have dendrites as the inputs. So in the biological neuron, we are also having the soma, that is called cell body, where the computation of the neuron will be happened. And we are also having the axon terminals. So if the neuron want to connect to another neuron, then these axon terminals will be connected, or it can also produce the outputs like y1, y2, so on, m number of outputs. And we can have x1, x2, so on, n number of inputs. So this is the basic structure of the biological neural network. Similarly, we are also having the artificial neuron. So here the cell nuclei where the computation of the neuron happening. And here we are having the computation, a basic computation like summing the wi and xi. Xi is the input, x1, x2, so on, n number of inputs, and wi is representing the weights associated with these inputs. So every input will have some weight. Based on these weights only, we can say that input can be passed fire to the next neuron or not. So based on these weights only, we are going to represent our model. So these weights will plays very important role. So when you are saving the trained model in the neural network, so these weight vectors only going to store into your memory. When you are getting the new inputs like x1, x2, so on, xi, these will be multiplied with the trained weights. So this we will discuss detailedly. This is now itself it is like a computational of the body of the neuron. And here we are sending the inputs like x1, x2, so on, xn in number of inputs, and the output of this cell body is connected with some activation function. So this is called some activation function where this f of x will get the output. So this activation function will tell you that this neuron will be fired, or this neuron will give you the classification output, or this neuron will be connected to next neuron or not. It will be carrying the information from one neuron to another neuron or not. All these things based on this activation function we can tell whether the neuron is activated or not simply. And next, this is the basic structure of the neural network. We have different neural networks like feed forward neural network and feedback neural networks are major architectures. So in the feed forward neural networks, we will see in the first scenario. So the feed forward neural networks, we are having the input layers, and we can have in between the output layer and input layer, we can have multiple layers. Those are called as hidden layers. So the input layers will be sending some information to the hidden layers, and the hidden layers will be passing some information to the output layer. So like this, the information is going to pass from one layer to another layer. So the edges between the hidden layer and input layer, and the edges between the output layer and hidden layer will be associated with some weights. So here, for example, if you consider input layer is having the 3 neurons and output layer is having the 2 neurons. That means your length of the features, number of features or length of the data is 3. Number of inputs is 3 you are passing. For example, you are teaching about a car object. So about the car, you have only three inputs. That means maybe the car name and size of the car and color of the car. So car name, size of the car and color of the car you can pass. So only with the car name, you cannot give more information, or you cannot classify completely about the car, because only you are passing the, oh sorry, only you are passing the simple information like a color and size, and also you can give name of the car. So only with the three features, you cannot classify completely about the car. So maybe if you are having only two outputs about the car, based on the name of the car, like it is a Maruti car, and Maruti company, or size of the car is medium size, or color of the car white. You cannot say about the car, you cannot classify that which type of car it is. We can have multiple models in the Maruti itself. So this is somewhat difficult. So if you are having more number of features, like if you are associated with the more number of neurons, increased input neurons, then I can easily classify. But still, if you are increasing the number of neurons, some kind of situations, it is very difficult to classify with more number of inputs. So you need to do much processing capabilities also. So there you can increase the number of hidden layers by giving more number of layers in between the output and the input. Such kind of situations we will see further. But this is the basic architecture of the feed forward neural network. And you have to remember that these connections are connected in fully connected manner. So each and every neuron is associated with the each and every neuron in the hidden layer. So first neuron is connected with the first neuron of the hidden layer, and first neuron is also connected with the first neuron or second neuron. First neuron is also connected with the third neuron, and first neuron is also connected with the fourth neuron. Like that, other neurons also connected with each and every neuron in the hidden layer. And similarly, from the hidden layer, we can also have connections between each and every neuron in the output layer. So this is called fully connected layer connections. So each and every neuron will be connected with the other neurons. So we are associated with the weights. In between these edges, we are having like W1, which the weight is passing from first neuron to the first neuron of the hidden layer, W11 we can represent. And from the first neuron to the second neuron of the hidden layer, W12, and W13, W1, and so on. Like that, we can have n number of neurons based on the number of neurons associated from input layer to the hidden layer. Like that, if you associated from second neuron of the input layer to the first neuron of the hidden layer, you can also have the weight vector like W21, W22, so on W2n. Like that, you can have multiple number of weight vectors. And after processing this weights computation, then we are going to store this weight vector as a trained model. Okay. So in the after you are getting the trained model, whenever you got the new inputs, you are just multiplying with the weights, like what we have seen in the previous slide. We are only multiplying the inputs with the associated weights. So you will get some output. If that output is having one kind of threshold, it will be belonging to one car. If that output is having another threshold, it is belonging to another car. Like that, you can give the prediction. So this is a simple computational things happening in the neural network. And one more thing you need to remember, if you are having three input neurons, and if you are having four input neurons in the hidden layer or next layer of the input layer, how many number of parameters will be trained in between this first layer and the second layer? So it is simply like m number of input neurons in the input layer will be multiplied with the n number of input neurons available in the second layer. So m by n parameters will be trained. So the number of training parameters between first layer and second layer will be m by n. Similarly, we can have again m number of neurons in the hidden layer and n number of neurons in the output layer. Again, m by n number of neurons will be trained in between this hidden layer and the output layer. This is the thing you need to understand. And you are having the two output neurons in the output layer. So you are only having the two classes. Two classes means, for example, you can classify only two categories. That will be like a Maruti Suzuki or Maruti Zen, maybe consider. Only two classes it can categorize. But if your input is not at all belonging to any of these two categories, then what will happen? So such things we will see later. So this is about the introduction of neural network. And we can also have the activation functions. We can also have the activation functions. What is this activation functions? This activation function will take you weighted sum of the inputs from the neuron. So whatever we are doing WIXI computation in the cell body of the neuron, that will be taken from the neuron and decides whether it should send to the signal from the this neural model or layer to the next layer. So it is useful when handling nonlinear activation functions or nonlinear problems. So what are all the nonlinear problems? Coming to here, we have given some kind of nonlinear problems here. So here the first one is linearly separable. For example, you have the data that can be classified with the linear hyperplane. That can be classified with the linear hyperplane like this. So you are having some kind of two categories like what we have seen, Maruti Suzuki or Maruti Gen 2 cars are there. You can easily categorize them because more differentiation. There will be the correlation between the two categories is very, very less. Then you can have much distance between the two data points. So you can easily categorize those features with the linearly separable line. Okay. So both the categories are linearly separable. So the features will be extracted and plotted on the 2D plane. Then you can easily differentiate with the linear hyperplane. So this is linearly separable problem. So such kind of issues, there will be no problem, such kind of problems like a linearly separable problems to classify with the simple neural network model. But some problems will be there. The correlation between the two classes will be very high. So some kind of features is very, very similar for the both the classes. Here you are having some data point belonging to the other class. Here you are having the data point we are belonging to other class. So you cannot classify such kind of problems with the linear hyperplane. So there you need some kind of non-linear hyperplane. So such kind of issues can be handled by adding multiple activation functions, non-linear activation functions. So we will see different activation functions we are having. And another example here you can see these are the data when you are plotted some features on the 2D plan. So this is also non-linear separable problem. So here you need a hyperplane, non-linear hyperplane like this. So then only you can classify them. Otherwise, it is not possible to classify. These are all some complex issues involved when you are classifying a non-linearly separable data. So if your data aligned in curved shape, it is a non-linear separable data. That is the basic thing you need to remember. So here we are having different activation functions. So first one, binary activation function. So in binary activation function, simply I can say it is like having the only two outputs in the binary activation function. So one is like 0 and another one is like 1. How this binary will act? So very simple. So you will have a threshold value and here x is the output of the computation that you are getting from the neuron. If you are having the neuron like 2 inputs and it has computed some value, and then you are getting the output value O. Okay, so let us assume that its output is X. So if X is greater than the threshold, if you are taking the threshold like a 0, if X is greater than 0, then it will be 1. If X is greater than or less than or equal to 0, then it will be 0. So either you will get the output of the binary activation function is 1 or only 0. Only 2 outputs can be possible. So this is the graphical representation like your binary activation. So here either the points will be coming like a 0 or you are only getting the 1. So this is very easy activation function. And next, sigmoid or logistic regression. Sigmoid or logistic activation function. So here simple, this function can take any real value. You can get any real value. That means your output of the WXA will be any real value, and this input can be produce the output values in between the 0 and 1. So for example, this is the curve of sigmoid function, and this is the formula for the sigmoid activation function. So whatever you are getting the value, for example, you got some value like 0.8 or something. So you can simply apply this formula, 1 by 1 plus e power minus of 0.8. So this computation, if you have done this computation, you will get the value in between the 0 and 1 only. So if your input is large, then you will get the output near to the 1. If your input is small value, small means here the small value, then you will get the output closer to the 0. But whatever the input is, whether bigger or smaller, you are only getting the values in between the 0 and 1. So it can also give the probability prediction, because our probability always will be between the 0 and 1. So you can also give the probability of predictions. Or if you are having the 3 classes, you can give the predictions. First class, how much probability will be there for giving the prediction as the first class, or second class probability, or third class probability. So such kind of things you can do with the logistic or sigmoid simple activation function. And next, we are also having the tanh activation function. So we can also call this tanh activation function as hyperbolic tangent function. Hyperbolic tangent function. So it is similar to the sigmoid function, but the range is -1 to +1. So the range of values you will get, output values you will get from -1 to +1. So it is better to compare the performance when you are using the sigmoid, or whenever you are using the tanh. You no need to simply say that tanh will give you the better result. So some kind of problems sigmoid will give the better result, and some kind of problems tanh will give you the better result, because the tanh range is wider than the sigmoid range. Simply because of that, you cannot say tanh will give always a better result than the sigmoid. You can see the tanh performance and the sigmoid performance. The only difference is it will give the values, activation outputs from the range from the -1 to the +1. So after the +1, again it will be saturated. There is no improvement or learning after the +1. So here the formula, when compared to the sigmoid and the tanh, it is very easy, like 2 by 1 plus e power minus 2x minus 1. Okay, so this is the tanh activation function. And we are also having the rectified linear unit, or we can simply call it as the ReLU. So this ReLU function is very popular and widely using in the deep learning and as well as machine learning applications. So for negative values, what it will do, it will give you as a 0, and for positive values, it will take the input as same. So this is the formula here. A rectified linear unit R of Z, output represent the Z, will be simply, you can say, max of 0, Z. If you are getting a Z value as a -1, so the maximum between the 0 and -1 is the 0. So that all the negative values less than 0 will become the 0 as the output. And if you are getting the greater than 0 value in the Z, so directly it will be passed as the output of the ReLU function. So the curve also you can see it will be like on 0, and it will be like incrementing like that in up to infinity. So this is the rectified linear unit activation function. So the range is very wide. So you are just eliminating the negative values in the activation outputs. We can get more number of outputs. The learning will be there. More number of approaches you can learn. There will be no saturation point like in we have seen in the sigmoid and the tan H. So after +1, there will be a saturation point for learning curve, but here the learning will be good in the ReLU. That is why it is very much popular. And also we are having another activation function like softmax. So this softmax, we can say simply, it is just a combination of several sigmoid functions. It is a combination of several sigmoid functions. So this softmax will be used to calculate the relative probabilities. So the relative probabilities, and like if you are having multiple classes, so multiple classes if you are having, you can use the softmax layer. So this is the formula for the softmax classification. E power z of j, that particular class, you can sum of all the probabilities like e power zk. So this will be simply represent in this manner. So for example, you are having 1, 2, 3, 4, 5. Your output layer is having 5 neuron values. So output layer is producing 5 values. That means you are having the 5 classes. Okay. So here, if you want to find out the probability corresponding to the first class, second class, third class category, fourth category, or fifth category, so you can do the same formula, apply e power 1.3 by sum of all the other categories. So you can do same e power 1.3 plus e power 5.1 plus so on e power 1.1. So you will get the normalized probability value among all the 5 classes, or categories. So the normalized probabilities will be in between the 0 to 1. So which will get the highest probability value, that category will be predicted as your output. For example, I have feeded some features about the car or a phone. So there are 5 classes I have given. I have given some input, and I am telling that first category about the car, second category about the phone, third category about something else. So the second category got the highest probability. That means the second category may be the phone. So the input that I fed to my model will be belonging to phone. So like that, the softmax activation function can be classified. If you have trained your model for 100 number of categories or classes, then easily you can also predict which type of category is much suitable for your input. So this is what happening about the softmax classification. And simply you can see here in the final output layer, you are having different classes like apple, bear, candy, dog, egg. So it will produce the probabilities for how much probability for telling this as a apple, how much probability for telling this is a beer, the input that I have fed to my input layer. So the input that I have fed to my input layer will be how much probability that it can be belonging to any of these classes. This is what the softmax layer will be working, and these are the about activation functions that we can apply. And in the next video, we will try to create a neural network, and we can also apply some kind of activation functions between the neurons. So with this, I can stop this lecture. Thank you.